In this video, I'm going to talk about two more operations of the single linked list, which are pop back and pop front. In my previous videos, I have talked about the push back method and the push front methods, and I discussed the time complexity required to write or implement those operations. So let's see how the pop back and the pop front functions work. Again, I will start with creating or drawing a linked list, a very simple singularly linked list, which, as we know, the very first node is always called head, and each node is connected through a link. Also, very quickly, I'm going to write down the very simple version of these two classes, which are the node and also the linked list. So I'm using Java as my basic language, or the language I'm going to use here. So a class node, which is generic, and the data will be from the type T, which will be specified later during the developing or creating an actual linked list. And then also the link to the next node, which again is from the type D, and I'm going to call this one next. We can for sure complete this code by adding constructors and maybe adding some setters and getters, but we're going to just see the very basic version of the class. And here also I have the class linked list, which also is a generic class, and then it's going to have the node header or head as the field or the instance variable. So let's see how the pop back and the pop front works. So again, we have two cases. For the first case, we're assuming that the linked list is empty or doesn't have any node. So if the linked list is empty, means that the header node is null. If the linked list is not empty, means that at least we have one node, which is a header, and we might have more than one. So let's implement the pop back method. And because the pop back we're going to return, or we're going to pop one value either from the back or front, the return type here is going to be from the type T, which is the kind of the data. Or sometimes maybe you want to return the whole node, but usually we just want to return the data rather than the whole node. So that's a pop back function, and here again we can check if header or head is equal to null, means that there is no node exists. So simply we're returning null because there's no node exists. And in the else statement, we're assuming that there is at least one node. So we can look at this diagram that we see here. We can look at this chart here, or this linked list here. And we're gonna write or implement the pop back. So as it is a single linked list, it means that we don't have access to the tail, and the only way to access the very last node, which is in other words we call it tail, is to start and traverse from the very first node and find the very last node. One thing is important here, that the very last node, although is required because we want to delete it, we also need the very second last node, which is this node here. And the reason that we need this node, because we're gonna make sure that this node here, which is this the very second last node, will not point to any other node anymore. Means that we're going to delete this connection that we have here. So I'm going to write a while loop statement. So while before that, actually I need to create a temporary node. So let's create a temporary node, which is again from the type T. Let's call it, for example, current node, or just TMP maybe, and at the very beginning it is just head. So what I'm gonna do, I'm gonna write while current.next is not equal to null, and then we're going to traverse and go to the next one. So current is equal to current dot next. So it's going to give me the very last node. However, I also need to keep the second last node as well, because that's going to be the last node after deleting the last node. So it means that this connection needs to go away. So for that, I'm going to create another temporary node to store the second last node. So I'm going to call it maybe second last node, and at first I'm going to put it to be equal to null, and anytime that I am just going to update the second last node, so second last node to be current before updating the current last node. So let's see that if it works properly or not. So at first I put the current node to be header. So here is my current node. So that's part of like the making sure that code works fine. So current is header, and also my current second last node is null. Then it says put the while the current next node is not equal to null, put the second last node to be current. So the current and the second last node will both point to head. However, the current node will be pointing to the next node. So this now is going to be my current node, but still this is my second last node. Then it goes here, while the current node next is not equal to null, it puts the second last node to be the current node. So that's will be the second last node, and it updates the current node to be the current last node. So that's going to be current next node. So there's going to be current. Then it says while current next is not equal to null, which is, so that means that there is no more node, and we found our last node, which is current node, and also we found the second last node here. So hopefully our code doesn't have any bug, and it's going to work perfectly. And after this, we're ready to actually do the delete part, or the part. So because I'm going to return the data of the last node, which is the current node, I'm going to write t and the data to be equal to the current dot data. So here again, I'm ignoring or skipping a lot of like details, such as encapsulation, and we're using setters and getters here. So I'm assuming that we can access the data. Maybe the better way to implement is just to write current.getData rather than writing current.data. But as you see here, I just ignore those part making this data or the next or head to be private. So I'm assuming that they are accessible, or again, it's just for the sake of like education, and we're not dealing with the like the implementation, too much implementation details. Now we got or stored the data of the current node, which is the last node, in the variable called d. And what needs to be done now is just to write second last node dot next to be equal to null, because we don't have any more node after this. So this second last node next will be null. It means that we're breaking this connection here. So I'm going to show it here. I hope that you can see that I'm deleting this connection here, and also this node is just gone. And at the end, because we kept the data of the last node, so we can simply just write return d, which was the data from the last node. So that was the pop back. As you see, we had to write a while loop structure for that. So in the best case, if the linked list is empty, or we have only one node, so it's going to be from big of 1. But in general, or in the worst case, if we have a linked list which is not empty, the number of operation depends on how many times we had to go for this while loop, which exactly is the number of items in linked list. That means that the worst case time complexity for the popback operation in a single linked list will be from the big of n. Again, we're assuming that we only have a header for linked list, and each node can only stores the next node and not the previous nodes. So now let's go to the pop front function. So again, it's going to return the data from the type t. So pop front, usually it doesn't have any parameter. And again, if the header is null, we're just returning null. So if header is equal to null, then we're simply returning null because nothing exists. So return null. And in the else statement, so going back to this example here, now instead of returning the deleting the last node, we're going to delete the very first node. So I'm going to draw the another linked list here just to have a separate example. So this time we're going to delete or pop the very first node. So this time is really easy because we have access to the next node of the header, which is the second node, and that's going to be our new head. So let's just keep the data of the header in some temporary node. So I'm going to write T and D, that is that our data are going to be head dot data. And simply I can just write head is equal to head dot next. So what's going to do is going to just delete or this first node here, and it's going to put the second node to be our new node. And I think we're done, and we just simply need to return just the D. Okay, so I'm going to explain this statement here that I have written again. So we are saying that put the header node or head to be the next node of the header. So means that we are going to lose access to this node, and this node that was the second node or the next node of the header of the old header gonna be seen as the header. So why we're saying that it's going to simply delete the first node? Because in our linked list we only have access to the header node directly. Every other node will be accessed through the next node in the single linked list. So this is gonna simply remove the very first node from the list. If you are using some other languages such as C, which we need to like the manually delete the memory, that's gonna be maybe a little bit more work, but in Java at least it's easier. We don't need to be worried about like this reference issue here. Just by writing this statement where we will make sure that we have removed the header node, and the second node will be the new node. So let's look at the time complexity of the pop front. As you see here, we have, if the header is null, we are only doing just a few operation. Also in the else statement, when the linked list is not empty, we're doing also a constant number operation no matter what is the size of the linked list. So that means the every case time complexity of the pop front is from the big O of 1. So big O of 1 for the pop front, and big O of n for the pop back, for the worst case of the pop back in a singly linked list, in case in which we only have the header node, and each node only knows its next node and not the previous node, and also the linked list does not have the tail node.